Welcome. We have a new problem at the screen and try to read the statement of the problem. That the statement is how high does the water rise on a vertical, a smooth wall? Of course, when it gets in contact with the wall, wall is smooth. If it wets it perfectly, that means here the angle between water layer and the wall is 90 degree. That is why we call it that it wets it perfectly. What is the force exerted by the wall on the water? And what is the radius of curvature of the water surface? At half the length of the rise from here, from this level, okay, in a plane perpendicular to the wall. So it's a kind of serious problem. Of course, we are going to solve this example by considering this water section. And we will be needing many things to solve it. That the surface tension of the water, its density, and also the horizontal thickness of the wall. I can't show you in this picture right now, but you can think water is not only vertical, it is also horizontal. The wall is not only vertical, but it's horizontal, and its horizontal thickness, I suppose it is equal to D. So we will need all this information to solve this problem. Though it is not mentioned in problem, but we are doing problem solving. We are not solving problems given to us, so we can ask that we need such terms. We can assume them and assume them that it is given, and you can see the things here. Three forces acting on this piece of liquid in horizontal direction. Of course, in vertical direction forces are acting, but they are pressure forces and they will get cancelled from outside to inside, so I am not going to take care of them. My focus is on the horizontal forces acting in the horizontal direction. And you can see here, there outside there will be the atmospheric pressure, and this horizontal component of atmospheric forces will be acting like this. And outside pressure is atmospheric pressure. I would like to call it P0, and this is acting in this direction. This force, this P0, the force F1 due to P0 should be written as P0 because pressure everywhere is constant from outside, and it is simply atmospheric pressure. So we don't need the average value of, because average value of a constant is the constant itself. So this will be pressure multiplied by area, and area is going to be H into D. Yeah, that's right. And you can see here, wall itself is going to apply pressure force from the left in this manner, in horizontal direction. And this pressure is varying. So if the pressure P0 is only here, and the rest of the part is inside the liquid, so pressure will keep varying, and we know that pressure at a distance x from the top can be simply written as P0 minus rho. Rho is the density of water, g, acceleration due to gravity, and that can be written like this. And you can see this decreases with the height or depth. So we need to find out the average value of this pressure, and so that this average value can be the Simply here you can write P naught only, because P naught average is P naught itself, because it's a constant value. Rho G X, so rho G can be taken out and X can be averaged from a value of 0 to length X, and its average value is going to be X by 2. So the average value is this, and this force from this side I would like to write F3, and this we had earlier F1, and F1 was simply P naught HD, and this F3 you would like to write P average HD, and there is one more force, and on this layer the rest of the water with surface tension sigma is going to pull the piece of liquid under examination to the right. This force I would like to F2, and F2 can be simply written as, it is applicable to all the water just right of it, and it will be perpendicular to the wall thickness, and it's going to be sigma multiplied by d, because it acts on whole length d. So this is force per unit length, and sigma d is the surface tension force. So and this will act towards right in horizontal direction. So now water block is in equilibrium, so the resultant of all the horizontal forces acting on it must be 0, and you can write something like here that P naught HD, that is the only force acting towards left, will be equal to sigma d plus this force F3, and F3 P average is simply P naught minus half rho G H, because H is the total length multiplied by HD, and you can see here, and you can find the value of H by solving all those things. P naught HD gets cancelled out, so you are going to get the value of H equals to sigma by rho Z, and you have all known water data and you can use it. The next problem is interesting, that is we need to find out the radius of curvature, and if you can see here in the picture itself, you can see there are two principal curvatures of water surface. One is 0 and another one is 1 by Rx. Rx is simply the radius of curvature of a smooth circle in a plane perpendicular to the wall. Oh, sorry, I'm talking to the people who read only NCRT or H.C. Verma kind of book plus 2 books. Sorry, I shouldn't have talked like this. So I'm going to explain you something first before finding the radius of curvature. One common manifestation of the surface tension is the is the difference in pressure it causes across a curved surface. For example, we can consider this section of water. And you can see here, this is a small section. I'm going to take it all and I will show you how is it small. I will consider all those things, and you can see here on this side the surface tension on water is acting in this direction, and on this side water is also acting in this direction. So since this length is quite a small, so I'm going to write here surface tension, that is force per unit length, as sigma, and here also as sigma, because this length is quite a small. What I'm trying to tell you, that for simplicity we consider first liquid surface which is curved in only one plane but is flat in a direction perpendicular to the plane. Don't understand? Then look at this picture. I took this picture. This is curved in one plane and flat in a direction perpendicular to that plane, which I can't show you right like this. You need to read Laplace-Young equation somewhere, or you can go and read it at a website called brannan.caltech.edu. You know, the website is caltech.edu, and Brannan must be somebody, either a student or an instructor or a teacher. So he can make Brannan, perhaps he can make his website on this caltech.edu, and I don't know, other things, you can read it here in the fluid mechanics section, Laplace-Young equation. So things might become more clear, very much clear to you. And this is the small section of this surface, and this is a small, so I'm going to make it a small by simply writing this angle is d theta and this angle is also d theta. Yeah. And the pressure in the different fluids, we have different fluids here also. This one is water and this one is air. So different fluids on the either side of the surface are denoted here as P naught. P naught must be normal to this surface, and P naught is P outside, and this is P inside, Pi. This is P inside, and that is acting from inside the fluid. And this direction is basically the normal direction, normal to the surface. So outward is the positive normal and inward is the negative normal. And the radius of curvature of this small surface is R. If I can think like this. So that this length can be simply written as R2RD theta. And now consider all the forces in the direction normal to the center of the fluid element, and the net pressure force acting in normal direction on this curved surface is it will be equal to P inside is always greater than P outside, and that will be P inside minus P outside into, this is the pressure force per unit length. I'm going to write pressure force per unit length, but because I'm going to equate it with surface tension, not with the surface tension force, I am going to equate it with surface tension, and that is force per unit length. So I'm going to write here the pressure force per unit length. Pressure force multiplied by length, pressure force multiplied by length I'm going to write here, not per unit length. And the length is this, and this you can see here, this length is R sine d theta. So, and the total length becomes 2R sine d theta. So this is the pressure multiplied by length of this curved section. And you can see here that this component of surface tension force of course on the two ends of this section of surface, which yields an inward force, and this is the surface tension force, surface tension. This is the surface tension acting in this direction, and we would like to take its component along the normal, and along the normal I think is normal will be in this direction, and perpendicular to the normal, that will be like this. And so I'm going to take this along the normal, that is this, and perpendicular to the normal, and you can see this angle will be d theta, because this is perpendicular to normal here, and this is the normal, and normal in this surface makes an angle d theta, so angle here will also be equal to d theta. You can see here. Yeah, this thing is perpendicular to this, I guess, or this thing is perpendicular to this line. Yeah, and this is along this surface, that means perpendicular to this line. So angle between these two things is d theta, so they are perpendicular. Its perpendicular is this, and its perpendicular is this, and that is will be also equal to d theta. So you can see here that the surface tension force, the surface tension acting on the two ends of the small section of curved surface will in an inward force, that means in the negative normal direction, and that is going to be s sine theta, s sine d theta. This is because this is just cos d theta, so it will become s sine d theta, and it will be equated by 2 sigma sine d theta. And in equilibrium you can write here 2r pi minus po sine d theta, and that will be equal to 2 sigma sine d theta. We can cancel these things. These are not zero, very close to zero, but they are not exactly zero, so we can cancel it out, and 2 gets cancelled out, and you can write here pi minus po, p inside minus the pressure difference created on this small section, that will be simply sigma by r. And yes, that means the surface tension causes a greater pressure inside the surface, and the difference in the surface tension divided by the radius of curvature. Yeah. And now we can solve simply our problem, that the pressure difference here inside the curve is like this, so P inside minus P outside will be simply equal to S, the surface tension divided by its radius of curvature. So the pressure difference at that point is this length is something h by 2 below, this distance is something h by 2 below. So you would like to write the radius of curvature simply like surface tension divided by pressure difference, and pressure difference at that point is simply rho gx, you can see here, and at h by 2, at x equals h by 2, you can put the values simply as sigma by rho g h by 2, and that will be the radius of curvature. And that's all, I think. We solved this problem. It took time because we don't have material like, if we don't have a spherical surface, we all know the pressure difference there is 2 sigma by r, or in case of soap bubble it was 4 sigma by r. But we don't have relation like any curve above for any curved surface that is not a spherical. So I needed to derive one equation, and it was not my derivation. I studied it on the website of caltech.edu, so I learned from here. Thank you very much for watching.